Wait a second. Okay, wait a second. Okay, sorry. Yeah, let's start. So, first, sorry. First, on Thursday, our TM Hongshu will give a tutorial on TensorFlow and PyTorch. So I highly recommend every student to join the lecture. If possible, you can first follow the documentation. Those are all online to install PyTorch or TensorFlow on your laptop, and then follow his um, follow the content and trying to run your TensorFlow or PyTorch scripts. Or later you can, because he's gonna share with you all the scripts um, after the class, so you can try to repeat his results. So I think that will be very useful, especially if you really want to use neural network to address your research or practical problems. You will never need to implement everything from scratch. You need to utilize the modern neural network library and functions to conveniently construct your neural network learning and tuning. Okay? And second thing is about the homework 5. So as you may have noticed, we have released the homework 5 today, and you have around like 17 days to finish homework 5. The workload is small. I believe it's even less than the homework 4. So I believe everybody should have sufficient time to finish that. But again, please do it as soon as possible, because we know that we're approaching the end of this semester. So you also need to take care of your project report, right? And also you have other classes, other homework and project due. So don't rush, again, don't rush on the last minute. Okay, so any question regarding the homework, project, and all those kinds?
Sorry, Professor. Can you repeat when is the time of class TensorFlow?
On this Thursday. On Thursday.
Okay, thank you.
What is the time? Time is just lecture time.
Okay, thank you.
Yeah, I mean, on Thursday's lecture, the lecture will be given by our TM. The lecture content, the topic is about how to use TensorFlow or PyTorch. Okay, any other question? And also, I believe you have to take a look at your the status of your project right now, because you need to give the project report. The due of the project report is also before the final exam. So yeah, again, please don't do it at last minute, because you have to allocate some time to review and prepare your final exam. Any other question? Okay, great. So let us continue. So first, let us spend about 10 minutes to finish up neural networks. So the last topic I want to talk about neural networks is the practice. There are a few practical concerns. Before that, we have given the definition of the neural network, and we talk about how predict with the neural network, namely the forward pass, right? How do you calculate neurons values layer by layer until we reach the top level to generate the output neuron value. Sorry. We'll use the output neurons value as our prediction. So the whole calculation is called forward pass. And then we talk about how to train a neural network. So the training of a neural network has the same framework as we train support vector machines or linear regression models. So basically, we use the stochastic gradient descent framework, right? So we just write down the loss function over the training set, where the loss function, the common use loss function can be the square loss, right? We just measure the square difference between our neural network prediction and ground truth output. And then the K is how to compute the gradient of the loss with respect to the weights in the neural network, right? So as we mentioned, the modern neural networks can be very large, meaning that it may contain like millions or even billions of parameters. So even calculating the stochastic gradient over a single training example, you have to compute the gradient for say millions or even billions of the weight parameters. So it's really, really expensive. So how can we address this problem? Right, the K technique is called backpropagation. Right? That's our focus. This is actually the most important part in this topic. Backpropagation essentially is a smart usage of the chain rule, right? So we calculate the gradient with respect to each neuron and with respect to each weight from the top layer to the bottom layer. That's why we call it backpropagation, right? So, and then we calculate this gradient and then catch them. And when we calculate the gradient with respect to the nodes and weights in the next level, we can utilize the previous calculated gradients so that we do not need to calculate everything from scratch. This is the key idea of the backpropagation. And and then once we have efficiently computed the gradient, we just plug into the stochastic gradient descent update. Right? In this way, we finish the training. We conduct the training of neural network. Right? So knowing those stuffs, we are already prepared to implement our own neural network training algorithm. Any question? Okay, so that's what you are required to do in your homework 5. So everybody is asked to implement the backpropagation by itself and then plug into a stochastic gradient descent framework with just on a very small data set, the banknote data set. Everybody is familiar with that, right? And want to see how whether neural network really works, right? And then, but the issue is that in the future, after this class, you might really want to use some neural network to address your fantastic problems, right? But what are the practical tricks you should know, right? If you want some tricks to improve performance, what kind of directions or what kind of efforts you should make, right? You should try to make. So those are something we want to talk about right now, right? So there are a few practical concerns of applying neural network. So mainly 3 aspects. So first, if you use stochastic gradient descent to do the training, what is the problem? So actually, this is related to the non-convexity and highly nonlinearity of the training loss, meaning that SGD may lead you to stack into some bad local minimum. How can we avoid them, right? And then the second problem is how can we prevent overfitting? Right? Neural network is really flexible model. It's very expressive. It can, in theory, it can approximate nearly any continuous function, right? So how can we prevent our model being overfitting the training data, right? And third thing is how do you identify the right structure of the neural network? Right? So let us talk about those points one by one. So first, what is possible issue of SGD, stochastic gradient descent? So one major problem is that it may oscillate or reach an inferior local minimum. But this is actually not the problem of SGD itself. This is actually the problem of the training loss of the neural network. Why? Because the neural network is using those rules, right? Linear transformation and nonlinear activation, then linear transformation, nonlinear activation. So after a few layers, such kind of linear, nonlinear transformation, your output of the neural network becomes a very complicated function of the input. So when you plug it into your loss function, your whole loss function is really, really complicated. It's, it usually is not non-convex, it's not linear. That means it can have many, many local minimums or local optimums. And if you use any algorithms, use gradient-based algorithms, usually you won't guarantee to reach a global minimum. This is different from our training of SVM or linear regression, right? Why? Why is different? Although they use the same algorithm framework, like SGD, why is this different from the training of SVM or linear regression model?
Different data.
Different data. Actually, even you apply your SGD on the same data, but for different models, they actually behave very differently. So I think the essence is not focusing on data. Any other suggestion? All right, so that's something we actually mentioned quite a few times, but might not raise your attention. So the key benefit of SVM or linear regression is that their objective function is always convex. Means that no matter what kind of initialization of your SGD you choose, although we always recommend you to start with 0, right? And but even if you start with some other random variables, and after convergence, in theory, all the algorithms will converge to the same global minimum, right? Because convex optimization, if it is convex, if it has a minimum, then it must be a global minimum, right? But for neural network, things becomes totally different because your neural network loss is non-convex, non-linear. I mean, it's different. That means it might have many, many local minimum, like something like this and like this, right? So different local minimum, they have their gradient to be 0, but they end up with being different function values. So perhaps one local minimum is good, showing corresponding very good generalization performance, but another local minimum is really bad. You actually don't know which local minimum you're gonna converge to. So that means you have to be careful about choosing how to initialize your model parameters. Usually, if you use neural network, you won't be in favor of 0 initialization. You don't initialize with to be 0. Usually, you have to initialize with some normal random variables or uniform random variables or truncated normal random variables. If you have time to take a look at the TensorFlow library or PyTorch library, they have some they have implemented a few commonly used initialization methods. That's really interesting. If you can take a look, right? And also another issue of training is the computational cost, as we mentioned, right? So neural networks, modern neural networks are usually very large, hundreds of layers, and millions or even billions of parameters at the same time. If you really want your network to work, you have to train them with a huge amount of data. So it is not surprising at all that you train your neural network with 1 billion images. It's nothing surprising at all. Google, Microsoft, Amazon are doing such kind of things every day. So That means even you use backpropagation, very, very clever algorithm, right? Your computation is still insufficient, the computational speed. And how can we address this problem? Maybe you haven't heard them before, right? So modern neural networks are trained based on specialized hardwares like GPUs, typical GPUs, right? And GPU is different from CPU. It's just used to processing the graphics. But right now, people found that it's very good to apply for the backpropagation kinds of algorithms. And Google has developed their own hardware to accelerate the computation of backpropagation. It's called TPU. If you're interested, you can take a look. You can try to apply it for account in Google Cloud. And if you are first time to use them, you have I don't know whether it still has that benefit now. But when I was the first user, I was given $300 credit. I can use them. I can use that to train GPU for, I believe, for 48 hours. So that's really good. GPU is much faster than GPU. And maybe you have heard that in iPhone, in the newest versions of iPhones, they have some Face ID function, right? They can recognize your face. So that face recognition technique is implemented by neural network, and to ensure their network to be fast, they actually plug into their specialized GPU in their in a iPhone. So if you have an iPhone 10 or iPhone 11, such kind of tiny chips are inside in your cell phone. Okay. And the third issue of the training with SGD is that it's hard to, rigorously detect the termination criteria, right? So ideally, so what is the ideal situation for my gradient descent approach to stop? Any thoughts? If you apply any gradient descent based approach, you can use stochastic gradient descent, you can use gradient descent, or any quadratic gradient descent, quasi gradient descent approach. So if you want to make your algorithm stop, what is the ideal way? Any suggestion?
The difference between two consecutive weight vectors is very small.
Yeah, that's one. That's definitely one criteria, right? But if you want to rigorously say, okay, I can stop, what is the condition?
Comparing loss values.
You mean compare with what? The function values?
No, loss values. Loss function.
Oh, yes. Yeah, of course. That's one way, right? But if you want to really justify that you have reached some local minimum, what is the final or optimal criteria or best criteria? So remember, we are using gradient-based approach, right? So theoretically speaking, if you really arrive at some local minimum, your gradient must be zero, right? So that means ideally, you should just look at your gradient and see whether they have a approach to zero, right? But can we implement such kind of testing using stochastic gradient descent in the stochastic gradient descent framework? Can we? Any suggestion? The answer is no, actually. Why? Because the motivation for choosing SGD is that we do not want to compute the exact gradient, right? Exact gradient needs you to compute the gradient of loss for all the training data points, right? Consider that you have like 1 billion training data points, right? To compute one full gradient, you have to go through the 1 billion training data points. That's really, really costly. Right? That's why we choose SGD, because we only pick up one or a many batch of training examples randomly, then calculate the gradient of their loss. We use that as a stochastic gradient, right, to do the update. So that means, okay, in practice, if we apply SGD framework, that means we are not able to compute the true gradient, right? That means we cannot use ideal situation, ideal condition to test whether we should terminate, right? Then why? Then when should we terminate? So here, a few commonly used approach, right? So the easiest one would be just set up the maximum number of epochs, like just set my maximum number of epochs to be 100. After running 100 epochs, no matter whether I really arrive at some local minimum or not, just terminate. And a more advanced criteria, including like I want to threshold in the training set error, right? This is actually costly as well, because if you have 1 billion training set, right? If I want to test whether I should terminate or not, I have to calculate the training error on this 1 billion data points. That's really costly as well, right? Or no decrease in error. Right? So another commonly used approach is take out a small portion of the training set randomly. We call it validation data set. So after we finish one epoch, and we just take a look at the error, test error on the validation data set. So we do this until we see, okay, the test error starts to significantly increase, then I'm gonna stop. So in practice, the termination criteria is kind of a combination of those choices, right? So, and in regard to avoiding bad local minimum, so we usually, in practice, people usually train with SGD using different random initial weights. You run SGD to train several times, and you pick up the one who has the best performance, or you just do the majority of voting techniques. So this is very similar to random forest, right? We train a bunch of classifiers, and then we just take the average of their prediction, or take the majority of their prediction. That's for binary or discrete classification. If you do the regression, you can simply take the average. Doing this can help us to improve the robustness of your classifier or the regressor, right? Okay, this is about the first problem. When you use stochastic gradient descent framework, what kind of practical issues you should be aware of, right? The second thing is how to prevent overfitting. Right? So, as we mentioned, right, training neural network is so expressive, right? So expressive, so flexible. So if you run many epochs on your training set, it may overtrain the network. That means you may fit the training data so good such that your generalization error becomes worse, right? So how can we avoid this problem? A commonly used approach to randomly sample a held out validation data set and just watch the accuracy after every epoch, right? So if the accuracy on the held out data set seems to decrease significantly, you're stopped. Right? And then you just trace back all the weights. So after each epoch, you're running so far, right? And pick up the weights who has the best performance on the validation data set. So this approach just assumes that the performance on the validation data set is kind of a surrogate of approximation of your generalization performance. But someone may argue that, okay, so if you just exclude a small portion of validation data set, you're gonna give up the information on those validation data set. I feel this is kind of a loss, right? I do not want to, I want to include all the information in the training data. I don't want to throw part of them. How can we how can we address this problem? We use kind of cross-validation technique. It's very similar to cross-validation, right? We use k-fold cross-validation where we just use each part. We use this validation data set. Then we choose the number of epochs who turns out to give the best performance on the held out data set, right? So if we use k-fold cross-validation, we have a k accuracies and k number of epochs. Then we just do the average. We use that as our best number of epochs. Then we train on the full data set with this best number of epochs. Any questions so far? In regard to those tricks to prevent overfitting? So everybody is comfortable? Okay, great. So those are about like utilizing held out data set and validation and k-fold cross-validation, right? But this inevitably you have to train, you have to conduct expensive training multiple times, right? So there is another famous trick, it's called dropout. Maybe you have heard it before. You don't need to do any cross-validation, you just train as usual, and the actual cost is very marginal. Dropout was invented by Jeffrey Hinton in 2020. It's a simple but a very effective trick. Maybe you have heard that. It's funny. Google is trying to apply the patent for dropout. That means other people cannot use dropout to avoid overfitting. So what is the trick of dropout? So just to train as usual, but the only difference is that during the training, at every step, we will conduct backpropagation to update your neurons and weights, right? So before that, you first use some probability rule to randomly preempt a portion of the neurons in your network. So say you can choose a probability, probability P. You can choose P to be 0.1, right? That means I just randomly select 1/10 nodes per layer in your neural network. I just preempt them, I just erase them, I just disable them, and also remove all the connections between them. And also the connections from them to other nodes. And then I just do backpropagation and do the stochastic gradient descent update on the remaining weights. That's for one update. Then when I process the next example or next mini batch of examples, I use this probability P to randomly select another portion of the nodes in your network and discard them and discard the weights associated with them, and then use backpropagation to calculate the gradient, calculate the stochastic gradient, and then update the remaining weights. So we do it again and again until we finish all the epochs. So this is a simple trick, but it turns out to work really well. So intuitively, you can imagine each update is actually optimizing or learning a simplified version of the original neural network, right? So you can imagine finally your prediction, your final prediction still use all the weights and all the neurons. Your final prediction can be viewed as an aggregation of many, many models. So it intuitively has a model averaging effect. So we know that if you do averaging, you improve the robustness, you reduce the variance, your variance component in your generation error. So it turns out to perform better. This is called dropout. Any questions so far? Okay, looks like everyone is satisfactory. We're on the same page, right? Okay, so finally, how do we identify the structure of the neural network? Right? How do we select the number of the hidden neurons in each layer, right? So obviously, the flexibility or the expressiveness of your neural network is determined by the number of neurons in each layer, right? If you choose too few hidden neurons, it might underfit data. Your model is too simple. You cannot well capture the complex patterns in your data. But on the other hand, if you use too many hidden neurons, your model becomes too complicated. It may overfit the training data. Right? So how can we identify the structure of neural network? The idea is similar to the cross-validation. Right? We can set up a candidate set of the number of neurons, and for each candidate, you just construct corresponding neural network and you run cross-validation to get accuracy. Right? Finally, you can choose the one who has the best accuracy. Right? So actually, those tricks are kind of based on manual testing and validation. Right? But nowadays, as I previously mentioned, people are trying to use smart techniques to automatically select the number of neurons, the number of layers, and all the other hyperparameters. This actually a research direction is called meta learning. So if you're interested, you can take a look. And in the web, actually, there are quite a few open source libraries which can help you to do the meta learning. As long as you have enough computational resources, you can just let them to help you select the best neural network for your data and for your application. Okay. So now we have finished up a neural network. So basically, we talk about the definition of neural network. Neural network is actually a hierarchical model, right? Each layer by layer, and also we obey some simple rules to construct the layers by layers until we reach the final output. But it turns out that by using these simple construction rules, your model can be highly flexible, right? And the key technique in training of the neural network is called backpropagation. This is something everybody must be familiar with, okay? Even in the future, you won't need to implement your backpropagation from scratch, but you, at least in your mind, you know what is the mechanism, okay? So this is just a simple or very preliminary introduction of the neural network because this is introduction to machine learning course. This is not advanced course. So that means there are a lot of content in artificial neural nets. It's a big topic. It's a very hot topic. So this is a vast area. It's fast moving. Many new algorithms and tricks for learning and tweak on a basic gradient-based method. For example, nowadays the state-of-art stochastic gradient-based approach is based on momentum. This is not the naive stochastic gradient descent. They add extra term to accelerate the convergence of your stochastic gradient descent update, right? And also, people by manually selecting or by automatically selecting, people have found neural networks with specialized structures, like restricted Boltzmann machines. Those type of neural networks are known to work well for dimension reduction, this kind of unsupervised learning task. Convolutional neural networks, right? Convolutional filters. This is a particular type of the activation functions. It turns out to work very effectively for imaging data. And also recurrent neural networks, like long short-term memory, like GRN, those kind of networks are specially designed to deal with sequence data, time series data, and many more, right? So, but with what we have discussed so far, you should be very convenient. You should feel very convenient and very easy to jump into any of those topics in depth, right? So, in the future, again, if you're interested, please feel free to look at the literature and try to tune those models. There are a lot of funny applications. Okay, so regarding neural network, any other question? No question? Okay, nice. Yeah. So again, on Thursday, I mean the day after tomorrow, our TM will give on the lecture time. Our TM will give the everybody joins the same lecture room. Right? We maintain the same Zoom lecture, so just use the link. But our TM will present the tutorial. So highly recommend you guys to join in. Okay. So let me share with you the new slides. Okay. So can everybody see the new slides about introduction to Bayesian learning? Okay, great. So now in the remaining a few lectures, we'll introduce another type of machine learning principle. It's called Bayesian learning or probabilistic learning. Right? So actually is another huge branch of machine learning topic. And as I told you, I'm focusing on machine learning. But if you ask me what is my specialized area is Bayesian learning or probabilistic learning. So you can call me a Bayesian guy. Right? I would love to be called a Bayesian guy. Okay. So before we introduce what is Bayesian learning, what is the key principle underlying Bayesian learning, right? Let us just review what we have learned so far to conduct learning, right? So we have seen a few learning principles, namely the idea is to construct the learning algorithm, to design a learning algorithm, right? So we have seen how we use mistake to drive our learning procedure. The typical example is the perceptron, right? We know perceptron is kind of online update. I will first test my prediction. If my prediction is correct, I'm not do any update. Right? I will only do the update until I make a mistake in predicting the current examples. That's why it's called mistake-driven learning, right? Another important principle we have seen is based on computational learning theory, namely pack learnability, right? So according to the pack learnability and the related theory like agnostic learning, we can derive some general sample complexity bound, right, to achieve a particular level of the generalization error under particular level of confidence. How many number of samples at least we should use, right? It's called sample complexity. And also, given a fixed number of samples with high probability, what is the upper bound of your generalization error, right? It's a generalization error bound. If you're trying to minimize your generalization error bound, this is called structure risk minimization, right? So a typical example of structure risk minimization is SVM, right? Is our focus, right? That's one of our focuses, right? So based on those principles, we can design learning objective, and you can develop your algorithms. And your algorithm is essentially a searching algorithm, right? You search over a hypothesis space, you want to find out the function. Each hypothesis can be viewed as function, right? Which given the input, you'll produce a prediction label, right? So what is Bayesian learning? Bayesian learning actually defines another way of learning. Bayesian learning actually gives you another principle to design a learning objective. So again, because this is called Bayesian, right? It's called probabilistic. So that principle must be stated in a probabilistic language, right? So we're going to introduce two typical learning algorithms in this regime. One is logistic regression, the other is called naive Bayes. Right? Logistic regression is very widely used. So don't think nowadays machine learning is dominated by neural network. Actually, neural network only takes a tiny portion of machine learning applications. You'll see in many online advertisements, logistic regression is the key algorithm. Although it's very simple, it was invented in the 1960s. Okay, so we'll first introduce the framework of Bayesian learning. So what kind of principles does Bayesian learning express, right? And what's the rationale? And then based on Bayesian learning principle, we'll introduce two ideas to estimate parameters. The first one is called maximum A posterior estimation. The other is called maximum likelihood estimation. So I believe many of you have heard these two words before. If you have taken statistics course before, you must have heard them before. You might also practice a lot of computation under these two estimation framework, right? And then I will introduce 2 examples. And again, if you have taken this course before, this will be sound very familiar with you. You must have done that before, okay? So first, what is Bayesian learning? Again, Bayesian learning is also called probabilistic learning. So very roughly, we can have 2 different notions of probabilistic learning. So the first notion has nothing different with our learning principle, previous learning principles, like mistake-driven or path learnability, whatever. But the only difference is that we restrict the type of the target function. The target function maps the input to a probability, namely a number between 0 and 1. That's the only difference. Then the remaining, and then you can apply any learning principle to learn this function. Like you can use path learnability, right? You can use mistake-driven. You can define whatever loss you want. You can define a loss function plus some regularizer on that. So then, what is the benefit of specializing the learning of the probability? So let us think about the classification problem, right? So remember, in our classification problem, our prediction function is a sign function. It's a sign. If you use linear classifier, your prediction function is a sign of your prediction score, which is a linear combination of your feature vector and weight, right? Plus a bias parameter. So, but here, if you choose to learn a probability concept, your prediction is no longer 1 or minus 1 or 0 or 1, right? No longer binary. It's just a continuous value, but except that this continuous value must be between 0 and 1. We will this output as the probability that your label is 1. It's not your prediction is the label. It's actually the probability that your label be 1. So now, can I ask what is the benefit you choose to learn such a target function? An idea? What's the benefit of using this? Can anyone please give me a hint? No one? It's too straightforward. Come on, give me some hint.
Flexibility of prediction.
Like what?
Flexibility of prediction.
Yeah, of course, flexibility of prediction, right? But in addition to that, any other benefit? So you can imagine, like right now, I can give you a score, right? This score not only represents the binary label 1 or 0, right? But also reflects how confident you are, right? If I give you a score 0.99, right? What does it mean? It means that I'm very confident that I'm gonna label this example to be 1, right? But if I give you the score to be 0.6, what does it mean? What does it reflect? And
Less likely to get 1.
Yes, exactly right. That means okay. Although I'm still gonna predict the label to be 1, but I'm not that confident, right? So actually, this is very important. In many decision decision applications, you not only need a hard decision like 0 or 1. You also need to tell how much confident I'm about my decision, right? If you're really, really confident, okay, I can trust you. If you're not that confident, I can tell you, okay, I only believe the label is 1, to have the chance 0.56. Do you really trust such kind of decision? Not yet, right? So that's the benefit. Okay, that's one notion of probabilistic learning. So it's nothing, you just apply all the previous learning principles, except that I'm gonna learn a probabilistic concept, meaning that I'm gonna map the input to the probability rather than a hard label, 0 or 1, right? So, but another notion, which is more widely researched and studied on Bayesian, is different. So it's called Bayesian learning. So it uses a different principle to select the hypothesis from hypothesis space. Right? So basically, it uses a probabilistic criterion in selecting the hypothesis. So the hypothesis itself is still a deterministic function, right? It's still a mapping from the input to some output. The output can be any value, can be continuous, can be real value, can be continuous, can be discrete, can be binary, or even can be some value between 0 and 1. It's okay, right? But here, the criterion according to which we select the best hypothesis is probabilistic. It's based on some probabilistic principle. So what is such kind of principle, right? So again, the goal is still to find the best hypothesis from some space H of hypothesis space, right? So given the observed data, right? But of course, different learning principle will tell you according to what principle is the best hypothesis, right? In Bayesian learning, we define the best to be the most probable hypothesis in the hypothesis space. It means that you have to assume some probability distribution over the hypothesis space, right? That means selecting each hypothesis in your hypothesis space has a different probability, right? And the goal is to find the hypothesis who has the largest probability. In other words, the goal is to find a hypothesis who is most probable to be the target or the true concept, right? So, of course, we use probability principle to select the best hypothesis. Then we need to construct such kind of probability distribution, right? How can we construct probability distribution, right? We also need to make a relationship between the observed data and this probability distribution, right? So now let us look at how we do that. But before that, let me first advocate the general benefit of Bayesian learning, right? So the general benefit of Bayesian learning includes the following, include but not limited to the following points. First, it provides interpretable learning algorithms. You will see that your model is based on some probabilistic procedure. You can use a probabilistic model to describe your learning model and also your searching procedure. It's not like black spot models. You apply some neural network. You don't know what happens in your layer by layer transformation, nonlinear transformation, right? And also the very important benefit is that it allows you to combine the prior knowledge with the observed data. So we will see when we construct the probability distribution over the hypothesis space, it is natural for us to combine our prior preferences and the data likelihood. Okay. And also it provides a conceptual framework to evaluate other learners and also provide tools to analyze learning. This is more directly related, like computational learning theory. There's one branch of computational learning theories called pack Bayesian. How do you combine the pack learnability with Bayesian learning framework to derive some new generalization error bound? How does it connect to a non-Bayesian learning approach? So this is a big area. The pioneer of this, the pioneer for this branch of research has been awarded a Turing Award probably 10 years ago. Yeah. So now let us review Bayes' theorem before we introduce what is how do we construct the probability distribution over the hypothesis space. Right? How do we find out the most probable hypothesis as the best hypothesis? Right? We need to review Bayes' theorem. Right? So the key of the Bayes' theorem is the Bayes rule. Bayes rule tells you how do you compute the conditional probability. Right? So the probability of the random variable y given the random variable x can be computed by dividing the joint probability of x and y by the marginal probability of x, right? So the joint probability can be further decomposed as the marginal probability of y multiplying with the conditional probability of x given y, right? So you can see through the Bayes rule, we actually build up relationship between these two inverse conditional probabilities, py given x and p of x given y, right? So I believe everybody is familiar with that. So this is essentially short for the probability of random variable y taking some specific value given the probability of given the random variable x taking some value, right? So now let us look at the structure of Bayes' theorem and want to extract some useful conclusion, right? So first, we found that in our decomposition of the joint probability in the numerator, right? So we have P of y. P of y actually represents the prior probability. Before we see the random variable x, what is our belief in y? This kind of belief or knowledge are encoded in this P of y, right? Now let us look at the second term, P of x given y. This is usually referred to as likelihood. So basically, it models or it describes what is the likelihood of observing x given y taking some specific value, right? So if we look at P of x, we found that this is essentially is constant to y, right? Why? Because it has it doesn't contain any x, right? It doesn't contain any y. So if you take a look at their calculation result, which is P of y given x, this is also referred to as posterior probability. It represents what is the probability of y given that x is observed, right? So you can see the posterior probability of y given x is observed as something is proportional to your prior belief of y multiplying with the likelihood of the observed x given y, right? So this structure gives us a convenient framework to integrate our prior knowledge with our observed data, right? So based on Bayes' rule, we have a bunch of rules to compute probabilities like product rule, sum rule, all those kind of stuff we have reviewed in our homework one, so I don't need to review it again. So if you feel unfamiliar, just look back to our homework one, what you have done in your homework one, right? So homework 0, right? So now after we have reviewed this basic concept, let us look at how Bayesian learning conducts the learning procedure, right? So in general, given data set D, the goal is to find the best hypothesis in our hypothesis space, right? In Bayesian learning, we use this conditional probability of the hypothesis given the observed data. We choose the hypothesis who has the largest conditional probability as the best hypothesis. Does it make sense? Any questions so far? Everybody's comfortable? Okay, great. It sounds pretty trivial, right? Okay, so now the question is how do we construct this conditional probability, right? Or in other words, you can view this conditional probability as a posterior probability. what is the distribution of the hypothesis given you have observed the training data set D, right? So here I want to emphasize, emphasize a few points that in case that you feel confusing about the definition of this probability distribution. So we can view, for better understanding, we can view D, the data set D, the D here is the event that we have observed this particular data set. And H represents the event that the hypothesis is a true hypothesis. That means this probability represents the posterior probability that H is the true hypothesis, given we have observed data D. Right? So in this way, you may say, okay, you assign such kind of probability is really natural, right? So to compute or to construct such kind of posterior probability, we can apply Bayes' rule, right? So in a denominator is the decomposition of the joint probability of H and D, and the denominator, this numerator, denominator is the marginal probability of the data D, right? So what does the prior probability mean? So the prior probability is actually the prior preferences over the hypothesis space. So before you have seen any training data, in your mind, you favor a particular type of hypothesis, and you're not favor of another type of hypothesis. So we can encode your prior preferences into this prior distribution over the hypothesis. And then the likelihood, right? So given a particular hypothesis, how do you model the likelihood that you observe this training data D? So from this Bayes rule, we can see that we can build up this posterior distribution of the hypothesis by multiplying the prior beliefs about the hypothesis before we see the data, multiplying with the likelihood of the data given specific hypothesis, right? That's how we construct the posterior distribution of the hypothesis. Any questions so far? Okay. So P of D, the marginal probability of the data, actually has nothing to do with specific H. So we can just view it as constant. So now I have introduced the concept of Bayesian learning, right? So what is the principle of Bayesian learning? Essentially, it uses the prior and the data likelihood to construct a posterior distribution over the hypothesis space, right? And then we search over this probability space to find out the hypothesis who has the largest posterior probability. That's the learning principle. Okay, so now, given this learning principle, how do we estimate the model, right? What is the way to find the best model parameters? So here I will give two commonly used approaches. One is called map estimation, the other is called MLE estimation, right? So let us first look at what is map estimation, right? The full name is maximum A posterior hypothesis, right? So basically, we want to, as we just mentioned, right, we stick, our idea, our goal is to find out the hypothesis who has the largest posterior probability, right? We maximize this posterior probability, and then again we use Bayes rule, right? We use Bayes rule. We find that okay, in the denominator, this P of D has nothing to do with the hypothesis. It's constant. We can just throw it out. This one is always positive. So if you throw it out, it doesn't affect your optimization, right? So essentially, maximizing, finding the best hypothesis is essentially to maximizing the product of the prior and the likelihood, right? So because posterior is proportional to prior multiplying with likelihood. So after we maximizing this product, we end up with this best hypothesis. We refer to this hypothesis as a maximum A posterior hypothesis. Okay?
I have a question.
Uh-huh.
Yeah, I'm confused about what the likelihood term represents. Specifically, why would the probability of seeing a given example change depending on what the hypothesis is?
Yeah, of course. Because in your probabilistic or Bayesian learning framework, you have to model everything with some probability, right? So you're gonna explain the observed data D is generated from some probability procedure. Suppose your hypothesis is this, and then following some probability model, you sample the data distribution, you sample the data D here. So obviously, the better the hypothesis, the larger the likelihood, right? For example, if you view your, let us take the random experiments, like if you toss a coin, right? If you toss a coin for 100 times, you end up with seeing 80 heads and 20 tails, right? And then you want to estimate what is the probability you have a head after tossing the coin, right? You have a lot of hypotheses. You have 0.1, you have 0.2, you have 0.9, you even have 1.0, right? Now the issue is that given any hypothesis, you can use that to model how likely your 100 coin tossing outcomes are, right?
Okay, yeah, that makes more sense.
Yeah. So
Thank you.
Yeah, the hypothesis is closer to the ground truth than the more likely, the larger likelihood, right? Okay. So now, obviously, maximum A posterior is fits is consistent with our Bayesian learning principle, right? So now let us try to simplify our setting. What if I assume the prior is uniform? In other words, I don't have any prior preferences over any hypothesis. I view each hypothesis in our hypothesis space equally likely to be the ground truth. Then P of H is kind of constant, right? Because P of H has nothing different with different H. Then when you do this maximization of this product, it is equivalent to maximizing P of D given H, right? That means you're only maximizing the likelihood. If you only maximize the likelihood, you get the best hypothesis. We call such a hypothesis as a maximum likelihood hypothesis. So you see the difference here, right? So the difference is that maximum likelihood estimation or maximum likelihood hypothesis doesn't care the prior preferences. Or in other words, it assumes that there's no prior preferences over any hypothesis. Every hypothesis is assumed to be equal likely to be the ground truth. And one practical issue. So when we do the real computation optimization, we usually don't directly optimize this product because you can imagine this probability, they are very small, right? If you do the if you maximize over them directly, you take a gradient, it's easy to have an underflow issue. So everything becomes zero. So usually we have to take a logarithm over them, then take the gradient to maximize them. Okay, we have introduced the map estimation and MOE estimation principle. So I assume everybody does not feel strange or feel weird about that because we might have heard of it like a million times, but we just want to refresh your mind or give you review them under new learning framework, right? So the remaining are two examples of doing maximum likelihood estimation. They're so common. You might have already practiced the same kind of examples, similar kind of examples many times. If you never heard them before, don't worry, just follow the slides and review them after slides. It's just some mechanical computation, but just allow you to apply such kind of principle to give you concrete examples. Okay, so we're gonna use maximal likelihood estimation to estimate a few parameters to see how it is applied to in concrete cases, right? So the example one is based on the so-called Bernoulli trials, right? So here is one fake scenario, right? Suppose one CEO of a startup hires you to do some consulting, right? So CEO gives you a problem. My company makes light bulbs, right? I need to know what is the probability they are faulty. You say, okay, sure, I can help you out. So are they all identical? And the CEO says, yes. And you say, okay, excellent. I know how to help. We need to do the experiment. So what kind of experiment? I just run and pick up 100 light bulbs produced by this startup, right? And just test them. It turns out that 80 light bulbs work, but 20 don't. Right? And then just report to CEO. The chance that your light bulb fails is 0.2. And CEO says, okay, wow, how do you know? Right? And you can start to explain. Right? So what is your explanation? What is your explanation? You just divide 80 over 100, or you just divide 20 over 100? Yeah, that's straightforward, but not enough. That's not sufficient. Okay, we need to explain how do you claim that 20 over 100 is reasonable, right? That refers to the Bernoulli trials, right? This is actually a classical probabilistic model, right? So we can assume that the chance that your one random light bulb fails is p, then the chance that it works is 1 minus p, right? So we're gonna randomly pick up 100 light bulbs to test, right? So each trial is assumed to be independent and identically distributed. This is a very reasonable assumption. And then the outcome of each test can be assumed to follow a Bernoulli distribution, right? And then we test it for 100 times, then the total probability that 80 work but 20 don't work is modeled in this form, right? So just choose 80 out of 100 and times p to the power of 80 and 1 minus p to the power of 20, right? So this is a formula of the probability of the Bernoulli trials, right? Now, by looking at the likelihood of the data, how do we estimate p? What kind of principle do we estimate p? Any idea?
Do we use Bayesian probability?
Oh, not using Bayesian probability. Actually, we have the probability, right? But here we know the likelihood of the data, right? But we don't know the p. But how do we estimate p? We maximize this likelihood, right? It's a basic assumption, right? So if it happens, it should be has the largest chance to happen, right? That's where the likelihood estimation, maximum likelihood estimation come from, right? So we maximize this likelihood to find the p such that make this probability to be the largest, right? That's how we estimate p. This is how we conduct maximum likelihood estimation, right? So we're gonna maximize this likelihood, and in general, suppose we have A bulbs work and B do not work, so we have a total of A plus B, right? So we want to find the best probability by maximizing the likelihood. So the likelihood, and again, we mentioned that we do not want to deal with the probability number, a small, tiny number closing to 0, right? We take logarithm. So logarithm probability, the probability is the number of choosing A out of A plus B times P of A, 1 minus P to the power of B, right? If you take logarithm, just throw out this constant, so it turns out to maximize A log P plus B log 1 minus P, right? So now you just set 0 to be 0, you solve this maximal likelihood estimation problem. The best probability is B over A plus B, right? So it is essentially the portion of the field lab ops, right? So it's kind of coincidence, but it's really interesting. You can just calculate the portion of the lab ops fulfilled. But the underlying assumption is that we use Bernoulli, right? Based on Bernoulli, we'll conduct n Bernoulli trials. But obviously, you could assume a different model. If you use different model, you end up with different maximum likelihood estimation. It might be not this simple and intuitive result. Okay. So now I want to look at another example, normal distribution, right? So again, but for normal distribution, we're actually assuming the data is continuous, right? So for our previous example, like Bernoulli distribution, we assume our outcome, our data are binary, right? Are binary and count, right? But for if you use a normal distribution, we're actually assuming our output, the data, the observed data are continuous, right? So suppose our hypotheses are comprised of real value functions. So given a d-dimensional input vector, our output will be a real number y, right? So we're gonna select a real value function out of from say 1 million functions or even infinite number of such kind of functions to fit the data, right? So now that we are using Bayesian learning, so we're gonna assume some probabilistic generation procedure about training data. Otherwise, we cannot construct the posterior probability of those hypotheses, right? So what kind of probability generation procedure we use, right? So we first assume the training input vectors are joined randomly, and then some kind of true function, the target function, is applied to get the prediction of f of xi. So remember, xi is random variable, right? F of xi will be a random variable as well, because the function random variable is also a random variable. And then the value is perturbed by some noise ei. And they're joined independently, this noise, are independent joined from some unknown Gaussian with zero mean. So this is usually assumption of Gaussian Y noise, right? The Gaussian Y noise is assumed to be sampled from zero mean Gaussian with some fixed noise, right? That means your observed output is this ground truth value plus some random noise, which follows unknown Gaussian with zero mean. This is how we assume the data are generated from some probability distribution, right? And say we have m training examples are generated independently from this procedure, right? So now, in the learning procedure, remember we're trying to search the hypothesis, right? So suppose we have a hypothesis H, right? So we want to know what is the probability that a particular label yi was generated by this hypothesis as h of xi, right? So we can take a look at the error. So the error will be yi subtracted by h of xi, right? So following our previous assumption, right? Yi subtracted by the ground truth example, ground truth output will be a Gaussian noise, right? Y Gaussian noise following some zero mean and fixed variance, right? So if your hypothesis is correct, then we should assume your error namely the difference between yi and your prediction, should also follow a standard Gaussian distribution with zero mean, right? That means we can model the likelihood of yi given your prediction h of xi as a Gaussian, with mean being your prediction h of xi, with variance to be the variance of your noise, right? Why? Because yi minus h of xi is a Gaussian, zero mean Gaussian, right? That means yi itself is a Gaussian with h of xi as mean, and variance doesn't change, right? It's just a linear addition of Gaussian random variables, still Gaussian, right? And now we haven't got the likelihood of the data given any hypothesis, right? Which is a Gaussian distribution with the mean being our prediction with variance to be some fixed value, right? So up to now, we just assume this is a fixed value. We do not ask that, but in general, you can also estimate the noise variance. It doesn't matter. So suppose we have m training examples, and each training example are generated independently. So their joint likelihood is the product of each individual likelihood, right? Now, to find out the best hypothesis, right? We just maximize the likelihood of the data given its hypothesis. That means we need to maximize this product of the individual likelihoods, right? Each individual likelihood is a Gaussian, right? It's like this. And again, we don't want to maximize the product of these values, because the product of this value is very close to zero. We don't want to do that. We just take logarithm to avoid numerical underfitting. So if we take a logarithm, then product becomes some summation, right? And you take a logarithm 1 over this factor and subtracted logarithm of the exponential, it just cancels. So you have a minus this square difference over 2 sigma squared, right? So remember sigma here, the noise variance or noise standard deviation is assumed to be a constant, so you can just remove them out, right? So you're gonna maximizing the summation of this square over square difference over each training examples divided by 2 sigma squares, right? If you just threw off minus sign, you end up with minimize this square summation, right? Summation of the squares. Right? Because sigma squared is positive and it's constant, you can throw it out as well. It doesn't influence your optimal results. So now let us look at through the Bayesian learning principle, the maximal likelihood estimation of a hypothesis is obtained by minimizing the summation of the square difference between your prediction and the ground truth. Right? What does it look like?
Square of errors.
Yeah, square variance, but it's not variance. It's actually the least square error, right? So this is actually the same principle as least square error. If you try to think about what we have done for the least square error, I try to recall that. If we consider our hypothesis to be a linear function, right? So that means each hypothesis is an inner product between the corresponding weak vector and input vector. And we plug in the form of hypothesis into our objective. The maximum likelihood estimation is obtained by minimizing the summation of the square loss, right? So this is exactly the same objective as we do the least mean square error for the linear regression, right? So the optimization is exactly the same. You can apply any stochastic gradient descent to do the things, right? So now we can see the interesting connection here, right? So on one hand, when we conduct least square method to do the linear regression, we construct loss, right? We choose the loss to be square loss. That is the difference between the ground truth and your prediction. Take a square and sum over all the training points. You get your training loss. You minimize it, you get the optimal weight vector, right? That's one learning principle. And as we mentioned in this class, we use Bayesian learning principle. The Bayesian learning principle is trying to find the most probable hypothesis, right? So construct a posterior probability distribution over the whole data set, but by assuming your prior is uniform, you'll end up with maximizing the likelihood of the data, right? If you assume your data generation procedure follows some Gaussian distribution, you can derive the same, exactly the same as objective, right? This is a very interesting connection. In other words, your least mean square method also has a probabilistic explanation. So actually, in many probabilistic learning paradigms, you'll find strong connection with other non-probabilistic methods. Either they are consistent in final objective function to optimize, or they have some asymptotic relationship. Any questions so far? Okay. Yeah, I'm happy to. Yeah, I'm happy to see everybody seems this seems quite straightforward to everybody. So to summarize, Bayesian learning is another framework to construct your learning objective. Although in many cases you will see consistency of their derived objective with the ones based on previous principle we have seen, right? So it's another way to ask what is the best hypothesis for a data set. So to conduct the learning procedure, we can do the maximum a posterior and maximum likelihood estimation. So MLE is a special case of MEP where you assume your prior is uniform. And also we have seen two examples of maximum likelihood estimation. One is based on binomial distribution, and one is based on normal distribution. Right? So you should be able to apply the both methods to ask model parameters, right? So in the next week, we'll introduce two typical learning models based on Bayesian learning. One is logistic regression, one is naive Bayes. Okay, so let us stop here. And again, please start to do a homework 5 as soon as possible, right away. And also, please come to our TensorFlow and the PyTorch tutorial on Thursday. Okay, thanks.